I have two topics that I want to talk about today, and I normally teach them complex numbers first and then sinusoidal signals second. The in-class assignment that we have is only related to complex numbers, though. So I think I'm going to do the sinusoidal review first, and then we'll finish up with complex numbers, and then we'll effectively be done with material for the day. For what it's worth, your in-class assignment that you guys are working today is meant to be an exercise in learning how to use your calculators correctly. So if you want to do it by hand, that's great, but I'm not expecting you to be able to do it by hand by any stretch of the imagination because you guys have calculators for a reason, okay? So I'll show you some of the tips and tricks for using your calculators with those virtual calculators that I have on my computer. All right, so let's kick things off by talking about sinusoids. Okay. So we're going to focus today on what the different parts of a sinusoidal signal are. And the reason why we are moving towards sinusoidal signals explicitly is because we are effectively done with our DC circuit analysis techniques and all of that kind of good stuff. So we're trending towards having an understanding of how electricity is distributed here in the US and most industrialized nations where we use AC distribution systems, meaning that all of our voltage sources and stuff like that, so our receptacles are actually supplying sinusoidal voltage signals that we use to power our everyday equipment and devices. Okay, so this is us just moving towards that. So I'm going to start by drawing a picture here, and I'm going to pre-apologize for my utter inability to draw a sinusoid that doesn't look like hot garbage. So I've got, let's just say for the sake of argument right now, that this is just a function x of t. It could be representative of either a current or a voltage. And it is going to be a sinusoidal function of time. So we might have something that looks like this. And again, I apologize for my inability to draw worth a damn. So something approximately like this would represent one period of a sinusoidal signal, okay? So this signal, x of t, could be expressed in one of two ways, okay? So we could write it as x naught cosine omega t plus some phase angle theta, or we could write it as x naught sine of omega t plus some phase angle phi. And we're going to talk about what those different constituent parts of both of those mathematical relationships represent, okay? So I'm going to start by defining our amplitude. I'm going to do that in red. So the distance between the horizontal axis and the peak value of our sinusoid and the distance between the horizontal axis and the negative peak value of our sinusoid is what's known as the amplitude, okay? And so this is a representation of the signal's intensity. So x naught is the signal's intensity slash strength. Actually, amplitude. Let's call it what it is first. Amplitude, which is a measure of the signal's strength. So, as a quick example here, the voltage that is being provided by every single receptacle in this classroom would be able to be represented by a cosine function or a sine function whose amplitude would be roughly 169.7 volts, which means the voltage that's coming out of one of those receptacles or sockets is oscillating between positive 169.7 volts and the negative 169.7 volts with some sort of periodicity that we'll talk about here in a moment, okay? So this is just effectively a scaling factor that lets us know how much larger than 1 this sinusoid is, okay? Now let's talk about omega. Okay. So omega is the signal's angular frequency. And it is always measured in units of radians per second. Haley, you okay? Nope, you're good. Okay. So we can't really see what omega represents on a single graph, but effectively what this is just telling us, like, it's a measure of how quickly we go through a single cycle. So the larger the angular frequency, the faster this signal oscillates between its peak values. Okay. So we can infer or mathematically determine omega using a couple of relationships that you guys might be familiar with already, okay? So I don't remember what's taught in Engineering 121 because it's changed probably fairly significantly since I taught it 5 years ago. But I remember you guys learning about linear frequency F, okay? Where linear frequency is measured in hertz, where a hertz is simply the number of cycles per second. Okay. And I also remember back from when I taught 121, we learned about the period of a function, where the period capital T is the amount of time it takes for one cycle to occur. So for this particular waveform, our period would be from here to here. So we're at whatever this value is and increasing at this point on the left-hand side, and we've returned to that same value and we're increasing at whatever point in time that is on the right-hand side. So I have attempted to draw exactly one cycle of our sinusoidal signal, and I have defined the period to be just the length of that cycle as a measure of time. So capital T period, lowercase f linear frequency, and lowercase omega angular frequency are all related to each other, okay? So capital T is something that we can observe from our graph. And it turns out that since capital T is the amount of time it takes for one cycle to occur, then that is the same thing as 1 over our linear frequency, because that's the number of cycles that occur in 1 second, okay? The relationship between F and omega, or linear frequency and angular frequency, is simply omega is equal to 2 pi times F. because our signal experiences a total phase shift of 360 degrees or 2 pi radians for every cycle. So we just multiply that linear frequency by a factor of 2 pi to get our angular frequency. So we can play around with these relationships a little bit as well, and we could see that omega is equal to 2 pi over the period if we were interested in being able to determine our angular frequency just by looking at our graph. So anybody have any questions, comments, or concerns about angular frequency, linear frequency, or period, or how they are related to each other? All right. So the last thing that we're going to talk about here then is our phase angles, okay? So theta and phi represent phase angles. Excuse me, they don't represent, they are phase angles, excuse me. So the reason why I used two different symbols, so theta for cosine and phi for the sine function, are because they're going to be two different numbers, even if they're representing literally the exact same signal, okay? So what our phase angle represents is effectively the amount of delay or the amount of advancement that our signal is experiencing, okay? So a phase angle is a measure of how delayed or advanced our signal is compared to a pure sinusoid. Okay. So let me explain what I mean by a pure sinusoid. And I'm actually going to extend my graph a smidge here to the left as well, because this will help us kind of sort some things out. All right, so when you guys think of a cosine function, without any phase angle, so just cosine of x or something like that, right? What is the value of cosine of 1? Or excuse me, cosine of 0? 1, right? So we would expect for a pure cosine function that it would hit its peak value at x is equal to 0, okay? Well, for this particular signal, it's hitting its peak value. Let me use a different color. And let me use an even different color than that. At some time later than t is equal to 0. And so I'm going to give this a subscript c, particularly because we're talking about how this is related for our cosine function, right? Because our expected value for cosine of 0 would be its maximum. And we see that it doesn't hit its maximum until some later point in time. What is the sine of 0? 0, right? So we would expect if we were representing this signal as a sine function, that it would start at 0 and increase from there. But instead, it's starting at some time less than 0. Let me do it in this color. And I'm going to call this delta t sub s because it's the change in time for the sine function, okay? So for our cosine function, we have effectively shifted that signal some amount to the right, okay? So we've shifted it by some amount onto the positive direction that we have for time. So that signal is considered delayed, okay? Because it hits its peak value at a later point in time than we would expect it to. So we have delayed the signal, right? For the sine representation, that signal is actually advanced because it's hitting its peak value before we would expect it to, based on the fact that it's hitting 0 at a time less than 0 when we would expect it to hit 0 at 0. I'm sorry if that's confusing, but effectively all of that boils down to positive phase angles represent an advanced signal. So I'm going to put time shifted to the left and our phase angle, arbitrarily theta in this case. Actually, it should be phi because that's our advanced signal, is going to be simply omega times delta t sub s, right? So let's just look at the units there really quickly. So we have our angular frequency omega measured in radians per second, multiplied by some amount of time measured in seconds. And so we're left with just something that is expressed in radians. So our phase angle is literally just an angle. Now, where things get a little wonky is that typically speaking, our phase angles are represented in degrees. So we have our angular frequency times time giving us an angle expressed in radians, and then we have a phase angle in degrees. And so we have to, and those are just the conventions that have been used forever. So we have to either convert omega times time into an angle in degrees or convert our phase angle into radians so that when we put this into our calculator or whatever, we have the same units on the angle, right? So I would personally choose to do this, to put it in degrees, as multiply it by 180 degrees per pi radians. So that's our conversion factor to give us this particular angle in degrees. Negative phase angles describe a delayed signal. And by that, I mean they are time shifted to the right. Okay. Where for our particular case, that would be theta is equal to negative omega times delta t sub c. And then I'll also use that conversion factor of 180 over pi to express that particular angle in degrees. Okay. So how do you guys feel about the constituent parts of a sinusoid? Okay. So let me just recap here. We can represent any sinusoidal signal as either a cosine function or a sine function. It will have some particular amplitude, which in this case I've called x naught. It will have an angular frequency omega, and it will have a phase angle, theta or phi. The sign that we, or excuse me, the symbol that we use there doesn't particularly matter. I just want to point out very distinctly here that you're going to get a different number for a sine representation than you will for a cosine representation. So if we're all okay with that, we understand the information that is carried by a sinusoidal signal, then let's introduce some trig identities and stuff like that that we're going to have to use over the next several class meetings. Okay. So I want to be incredibly clear here. I am going to use several of these over the next couple of days. I'm going to make explicit notation of which ones I actually expect you guys to know for your exam. And that list is going to be incredibly short, okay? So I'm about to hit you with like 11, and I'm going to expect you to know maybe 3, okay? So the first one, what did I just do? So our first trig identity is the sine of omega t is equal to the cosine of omega t minus 90 degrees. So effectively, a cosine function is nothing more than a sine function that is time shifted to the right by some amount, which we can very obviously see just from looking at the damn graph. Okay, so that's our first trig identity. And our second trig identity is effectively just going the opposite direction. So cosine of omega t is nothing more than sine of omega t plus 90 degrees. Right. So we can get a sine function from a cosine function simply by shifting to the left by 90 degrees. And if let me go a step further here. That's our simplified version. So we could then say that sine omega t plus some phase angle phi is then going to be cosine omega t plus phi minus 90 degrees. Where this phi minus 90 degrees is theta, the phase angle of the cosine function. Very similarly, we could say that cosine of omega t plus theta is simply sine of omega t plus theta plus 90 degrees, where theta plus 90 degrees is just phi, our net phase angle for our sine function. So using these two identities, we should be able to go back and forth between sine and cosine function very easily. Just to recap things, if we want to go from sine to cosine, we subtract 90 degrees from the phase angle. If we want to go from cosine to sine, we add 90 degrees to the phase angle. Everything else stays exactly the same. Omega will not change, amplitude will not change. The only difference between a sine function and a cosine function is the phase angle, okay? So another identity that can be useful is what happens if we have negative sine omega t plus some phase angle phi. Okay. So if I want to get rid of that negative sign out front, all I have to do is either add or subtract 180 degrees from the phase angle, because that's effectively us just shifting things by exactly half of a cycle, okay? So this would look like sine of omega t plus phi plus or minus 180 degrees. It does not remotely matter whether we add or subtract that 180 degrees, because that's either a shift of half of a cycle to the right or a shift of half a cycle to the left, but it still gets us the exact same point, okay? Our fourth trig identity is then effectively this exact same thing, but for a cosine function. So if we ever have negative cosine omega t plus theta. We can get rid of that negative sign, just like we did for the sine function, by simply having cosine of positive omega t plus theta plus or minus 180 degrees, excuse me. Let me make that 180 look like I didn't start writing 90 on accident. So that's how we can get rid of negative signs on our amplitude. And the reason why I'm bringing that up in particular is because some of our calculators will have an absolute panic attack, especially when we use complex numbers, of having an amplitude with a negative value. That is the same thing as just shifting the phase by 180 degrees. Okay, so if your calculator has a panic attack, just add plus or minus 180 to your phase angle and you're good to go. All right, so the ones that I expect you to be able to apply in this particular class at the drop of a hat are this guy right here. So converting a sine function to a cosine function, because electrical engineering uses the cosine function as its basis for all sinusoidal steady state circuit analysis for reasons that I will discuss here shortly. And then this guy right here, where if I need to get rid of a negative sign out front, I simply shift my phase by 180 degrees. So if I know these two things, I can put any possible sinusoidal signal as a cosine function with a positive amplitude. Okay, so these are two incredibly important ones that I expect you guys to just fundamentally know by the end of this class. The next four that I'm going to give you, I'm going to use a whole heck of a lot Friday, and then we will hopefully never use them again. Okay, so I just want you to know where they're coming from. So the first one is sine alpha plus beta. Okay, and so this is going to be equal to sine alpha cosine beta plus cosine alpha sine beta. So if I have a sinusoidal function effectively that has the sum of two arguments, like, I don't know, one of them is maybe omega t and the other one is a phase angle, I can decompose that into a pure sinusoidal signal, so sine alpha multiplied by the cosine of beta, where if beta is my phase angle, cosine of beta is literally just a constant. And then same thing on the other side. I have a pure cosine function multiplied effectively by a constant. Okay. So this allows me to get rid of my phase angle by breaking my sinusoidal signal up into two pure sinusoidal terms. Similarly, sine alpha minus beta is simply sine alpha cosine beta minus cosine alpha sine beta. So if I flip the sign on my operation there inside the sine function, it just flips the sign on how I split it up. Number 7 is cosine alpha plus beta, and that is equal to cosine alpha cosine beta minus sine alpha sine beta. And just to be clear, I did not mess up the negative sign there in the middle. Cosine alpha plus beta should have a negative sign on the right-hand side of the equal sign there. And then lastly, for these guys, cosine alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. So I'm just going to put a bracket here and say, Dr. Hartman will use these next class. I do not expect you guys to know them. Realistically, you can use them for your homework assignments and stuff like that, but my goal is to show you a better, much more simplified way than getting through with all of these terrible trig identities. So I will punish myself to prove to you that using trig is a terrible idea. Okay. All right, 2 more and then we're done. So cosine alpha times cosine beta will be equal to 1/2 cosine alpha minus beta plus 1/2 cosine alpha plus beta. We are not going to see this one used for quite some time. But when we get into our power relationships for sinusoidal signals, this guy is going to show up literally everywhere. There's also a rule for sine alpha times sine beta or sine alpha times cosine beta, but because we can convert any sine function into a cosine function, we really can do everything with that one single identity. So I never bothered learning the other ones. And then the last one here is, in my opinion, probably one of the most important equations in all of electrical engineering, okay? This is what's called Euler's identity. If I was to ever get a tattoo, it would be related to this thing. That's how important I feel it is, okay? So Euler's identity tells us that cosine omega t plus some phase angle theta plus j are imaginary operator. You guys literally don't know what that is just yet, so I'm going to make a note here. J is simply equal to the square root of -1. In your math classes, you would probably taught that as I. We can't use I in electrical engineering to represent that because I is for current. So we call it J, even though literally no one else does. So anytime you see a lowercase j in a context of electrical engineering, it's just the square root of -1. So cosine omega t plus theta plus j times the sine of omega t plus theta is equal to e to the j omega t plus theta. So this rule effectively tells us how sinusoids are related to complex numbers. And this guy right here is another one of those critically important things. So those are the 3 out of the 10 that I really expect you guys to know by the end of this class. Okay, so I've introduced complex numbers here, but I'm not quite ready to really get into the nitty-gritty of that before I introduce 1 or 2 more short topics related to sinusoids, okay? So let's go ahead and take care of those really quickly. So the first thing that I want to talk about is comparing sinusoids. So that will be something that we will do relatively regularly as part of our analysis and all of that kind of good stuff, okay? And effectively, I'm just going to show you guys what the rules are, okay? So the first rule for comparing sinusoids is that all signals must be expressed explicitly, sorry, I'm misspelling it. All signals must be expressed explicitly as either cosine or sine functions. So let me explain what I mean by that really quickly. So let's say that I have some voltage signal VA of t is 8 cosine 17t plus 15 degrees volts, and VB of t would be 11 sine 17t plus 45 degrees volts. In order for me to compare these signals to each other, I need to express the cosine function as a sine, or I need to express the sine function as a cosine so that they're all cosines or they're all sines. I can't have them mixed up, or I can't do an apples to apples comparison, okay? So as I mentioned a couple of moments ago, electrical engineering uses the cosine function as our basis for all sinusoidal signals. For what it's worth, it's just because it's the real part of a complex number. So I would convert this VB into VB of t is 11 cosine 17t minus 45 degree volts, and then it'd be good to go. So just to be clear, literally all I did was I subtracted 90 degrees from the phase angle to go from sine to cosine. Don't have to do anything fancier than that. Now they're both cosine functions, and I can compare them to each other. My second rule is that all signals must be expressed with positive amplitudes. Okay. So if I had a signal VC of t that was -6, let's just do cosine. Cosine 17t minus 100 degrees volts, I would need to use, I think, trig identity number 4 from the list that I gave you to be able to represent this as VC of t would be +6 cosine 17t, and now I can either add or subtract 180 degrees. I'm going to choose to add 180 degrees just so that this number is smaller. That's the only reason I'm doing it. I could have just as easily said that that was 6 cosine 17t minus 280 degrees, and it would literally represent the exact same thing. Okay. Our last rule for comparing sinusoids is that all signals must have the same frequency. Doesn't matter if they have the same angular frequency or the same linear frequency, since those guys are just related to each other by a constant, but they must all have the exact same frequency. There is no trig identity that can fix this for us. So we either have signals that have the same frequency and thus can be compared to each other, or we do not. Okay. So those are 3 basic rules for comparing sinusoids. And now I want to talk about probably the most common comparison of sinusoids that we see, particularly in steady state sinusoidal analysis and power related engineering. And that is the concept of leading and lagging. Okay. So I'm going to give us 3 signals to work with. Okay. So I'm going to do them in 3 different colors. So let's say that I have a voltage VA of t is equal to 10 cosine 6 pi plus 30 degrees volts. VB of t is equal to 15 cosine, sorry, that should be 6 pi t. Without the t, it doesn't really mean anything. It's just a constant. My apologies. 6 pi t minus 15 degrees volts. And lastly, Vc of t will be 5 cosine 6 pi t plus 120 degrees volts. So due to my inability to draw a single sinusoid, I feel like me trying to draw 3 of them on the same graph is going to be an absolute nightmare. So instead, I'm going to rely on Desmos to help me graph these things and make them look slightly less shitty. Okay, so give me just a moment here. So my first signal was VA, right? I swear there's a way. I'll just write it as VA. And I'm going to do it of X because I don't remember how to make everything as a function of time. So that's not good. I'm not going to bother with it. So this was 10 cosine 6 pi. And then what was the phase angle? Plus 30. Okay. So right now, that 30 is in degrees. I'm going to convert it into radians. So I'm just going to multiply that 30 by pi over 180 so that it's just converting that into radians. Why is it? Okay. So I'm going to call it V1 now, apparently, because VA doesn't work, but V1 does. And I'm going to change my settings here slightly because it's just got so many oscillations on the graph that it's looking gross. Okay. So I know that the peak values that I'm looking at are going to be roughly in the plus or minus 15. So just for the hell of it, I'm going to do negative 20 to positive 20. And because I've got an angular frequency of 6 pi, I'm going to do this from, let's see, negative 1-ish to positive, positive 5 is still too much. Let's do positive 3. So this looks a lot less horrifying to look at, I think, okay? So there is VA. And what color did I use for that? Was it red? I'll be damned. Let's do VB, which I'm going to call V2. And this was 15 cosine 6 pi t, excuse me, x. What was the phase angle for this one? Minus 15. And then once again, I'm just going to multiply by pi over 180 so that I get that everything expressed in radians. Was the color for that one blue? All right. And then let's see if I hit the lottery and the color for this one shows up as green. I think it will. V3 of x was 5 cosine 6 pi t x plus 120. All right. So these are our 3 graphs. There is a lot going on, so I actually might make those settings a little bit better on our part. So I'm going to do from like negative 1/2 to positive 1. Ooh, good God. I accidentally put it back to the default settings, which is very much not what I wanted. All right. So we have a better depiction of what's going on. Okay, so we can see a couple of things here really quickly, right? So our green curve is obviously an advanced value because everything is being expressed as a cosine function, and the green curve hits its peak somewhere around negative 0.1. The red curve is also an advanced signal because it's hitting its peak before x is equal to 0. And the blue curve is slightly delayed because it's hitting its peak slightly after x is equal to 0, okay? So I could say that the green curve is leading both the red curve and the blue curve because it's hitting its peak value at an earlier point in time. Now, you could very obviously make the argument that, hey, the green curve here is hitting its peak value after this peak on the blue curve and this one on the red curve. And there's nothing particularly wrong with that. But generally speaking, we want to be looking at the peaks that are closest to each other, okay? Which would be, this set right here, or this set of 3 peaks right here, or this set right here, right? So we can argue one way or the other, and the math will bear out either way. And I'll show you what I mean by that here in a moment. But if we're just looking at the peaks that are closest to each other, then we could say that the green curve is leading the red and the blue because it hits its peak value first. The red curve is leading the blue because it hits its peak value before the blue, but it is lagging the green because it hits its peak value afterwards. Okay, so let me write this stuff down so that we have something to kind of go on here. So a waveform leads another signal if it hits its peak value earlier in time than the signal it's being compared to. And we can say that a waveform lags another signal if it hits its peak value after or later in time than the signal it's being compared to. Okay. So let me go back to Desmos here. So we can see from this plot, which is going to be something pretty similar to what you might see on an oscilloscope when you're actually measuring time varying voltage waveforms and stuff like that for sinusoidal steady state systems. So we can see pretty easily which signal is leading, which signal is lagging, and that kind of thing. But I particularly find it difficult to quantify by how much signals are leading and lagging using a time domain representation like this. Okay? So instead, I like to use what is called a phase diagram to do all of my leading and lagging analysis. Okay. So a phase diagram is literally nothing more than a snapshot of these signals at a particular point in time. And you can use any point in time you want. However, I and the overwhelming majority of engineers use t is equal to 0 because that throws away that 6 pi t part, and we only have magnitudes and phase angles to look at. So it makes it significantly easier. Okay. So if I were trying to make a phase diagram for these three signals, it might look something like this, okay? So this would correspond to 0 degrees. This is positive 90 degrees. This is plus or minus 180 degrees. And this is negative 90 degrees. So my red signal would be something akin to this, where this angle right here is just 30 degrees. So it arguably has a length of 10 units. That actually doesn't particularly matter too much. What's really important is the phase angle compared to 0 degrees is positive 30. Okay. My blue signal, I could represent on a phase diagram like so. And lastly, my green signal would be somewhere over here. So I've drawn my phase diagram. Now, effectively, here are the rules for using a phase diagram. If we want to measure lagging, we go clockwise. And if we want to measure leading, we go counterclockwise. So let me write that down. So effectively, when we're looking at lagging, we're looking for a more negative phase angle, meaning more of a delay than what our reference is. And when we're looking at leading, we're looking for more positive of a phase angle or advanced compared to our reference signal, okay? So if I wanted to find, let's just do a quick example here. So by how much does A, B, or C? Pick A. Leading or lagging? Somebody else pick. B or C? B. All right. So by how much does VA lag VB? So VB is my reference, okay? So I'm going to start my measurement at VB, and I am just going to go around in a clockwise direction until I hit VA. So to me, I have 90 minus 15, so that's 75 degrees here, 90 degrees here, 90 degrees here, 90 minus 30 here. I'm going to add all those together. So 90 plus 90 is 180, plus 60 is 240, plus 75 is 315 degrees. So in your homeworks, on your exams, all of that kind of good stuff, the second signal in the expression is your reference. That's where you're going to start your measurement. If you are measuring lagging, you go clockwise. If you are measuring leading, you go counterclockwise. I want to pull up the web work assignment here, and we're going to work a couple of the examples together. This is from homework set number 19, which I'm going to assign it to open to you guys today, as well as homework set number 18, just in case you want to get ahead of the game slightly, since we're covering the majority of the material today anyway. And I want to make you aware, as if you aren't already aware, that web work is terrible. So if we look at homework set number 19, and I think it's problem 2, but we'll see. Nope. Maybe it was problem 1. Yeah, problem one. So we're asked to find the angle by which I1 lags V1 if V1 is 191 cosine blah, 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 minus 92 degrees. Okay, so let me just come down here. So I'm just going to write these signals down. So here's V1 of t, and it was 191 cosine something, doesn't particularly matter. 120 pi t minus 92. And then I1, I will do in blue. And I'll give you guys the option. Are we going to do part A, part B, or part C? B. Okay. So 4 sine 120 pi t minus 64. All right. Yes. So this is a comparison of sinusoidal signals. So I need to convert that sine function into a cosine function. So that's going to look like 4 cosine 120 pi t. What comes next? So hit me with a number. So to go from sine to cosine, we subtract 90. To go from cosine to sine, we add 90. We are going from sine to cosine. So 64, negative 64 minus 90 is negative 154, right? Did I do that mental math correctly? So those are our two signals. The question that we are asked, to be clear here, is find the angle by which I1 lags V1. So I'm going to draw my phase diagram over here on the right. Once again, I have 0 degrees, 90 degrees, plus or minus 180 degrees, and then negative 90 degrees. So my voltage signal should be something like this, right? Where this angle is 92 degrees away from my 0 degrees thing. So this is V1. My current is at negative 154 degrees, so that would be somewhere in this area. Doesn't particularly matter how accurately I draw it, just that I get the numbers correct, okay? So this is 154 degrees. And there is, excuse me, that should be I1. Okay. We're finding the angle by which I1 lags V1. So V1 is our reference. So we're going to measure from V1 until we hit I1. So to me, that's just 154 degrees minus 92 degrees. 60, 72? Maybe, no, that's not right. 62. 62 degrees. Are we okay with that process? Let's start there. All right, there is a very distinct possibility that web work is going to tell me that I am wrong, even though I, as a conceited gentleman, feel like I did this problem absolutely flawlessly, okay? So let's see what web work says. So I'm putting in 62 degrees right here for part B, and I'm going to check my answer. Oh, well, son of a bitch, it said it was right. I was expecting it to not to. Okay, so let me tell you guys what the issue is, even though it This is the only time that I've ever taught this class where this didn't bite me in the ass. Of course, it's going to be in front of you again, but that's okay. The way that these are coded, they are expecting a fixed angle, okay? WebWork isn't smart enough to determine equivalent angles. So if this answer had told me that I was incorrect, the only thing that I would do is I would add 360 degrees and see if that is correct, or subtract 360 degrees and see if that is correct, because they all represent literally the exact same angle. It's just WebWork was coded poorly and I'm not smart enough to fix it. So if you're following the process that I have given to you, you are doing it exactly right. Add or subtract 360 degrees when WebWork tells you you're wrong, and you will get the right answer, okay? It's just because WebWork isn't smart enough to realize 0 and 360 and negative 360 and positive 720 and negative 720 are all the same thing from an angle standpoint. Okay, so how do you guys feel about the leading and lagging stuff? Fairly straightforward once you understand the rules. Okay, I am done sinusoidal review stuff. We're done with that. Now let's get into the complex number part, which is arguably more fun. We'll see. Actually, while I'm at it, let me go ahead and open up various calculators. Let me open up the Casio 115 as well. Continue with the current version. Oh my God, I only have 1 day left on the trial version. I don't want to pay for this. All right, so I've got those things open. Let me just clear everything out. And we'll go from there. Okay. So, put very simply, a complex number is nothing more than a number that has both a real part and an imaginary part, okay? So I'm going to draw a complex plane in the middle of my screen. Like so. The horizontal axis is where real numbers live. So this is literally just the number line that you guys learned about in probably second grade or something like that, right? Stretching from negative infinity all the way to positive infinity. That's our x-axis. Our imaginary axis is the vertical axis. And so this is just another number line that's just been rotated by 90 degrees, okay? So if I have a rectangular form complex number, I might go out some number of units in the real direction, which I'm going to call that A, and some number of units in the imaginary direction, I'm going to call that B. And so my complex number, capital A with a bar over it, would simply be A plus JB in rectangular form, right? So I have a distinct real part and a distinct imaginary part. So let's get into the details there. So the real part of complex number A is simply lowercase a, and the imaginary part of complex number A is just lowercase b. So you can think about this just like simple two-dimensional vectors, right? You've got a real dimension vector and an imaginary dimension vector, okay, or imaginary direction vector, okay? So rectangular form is very, very simple, okay? There are also two other ways that we can choose to represent complex numbers. They are the exponential form and the polar form. So I'm putting the exponential form and the polar form both on the right-hand side here because they contain literally the exact same information. Polar form complex number is just a shorthand notation for the exponential form complex number, okay? So in our exponential form, we have some magnitude, and then we also have some angle formed with respect to the positive real axis. So our complex number A in exponential form would be the magnitude of A, that's just the length of that vector, e to the j theta A. And in polar form, we would simply write that as A angle operator theta A. Any questions before I move on and talk about how we can go from one form to the other and all of that kind of good stuff? Declan?
What's the angle?
So an angle operator is literally, it's a button on our keyboard or on our calculator or whatever. And it effectively is just saying our polar form complex number has two constituent parts, a magnitude and a phase angle. And that angle operator just tells the calculator the next part is the phase angle. That's it. So for what it's worth, your calculator only deals in rectangular form complex numbers and polar form complex numbers. If you try to put in an exponential form complex number, it will 100% of the time give you a math error. It does not matter what model of calculator you have. They only accept rectangular and polar. So if I ever give you an exponential form complex number, I expect you to be able to get that into the polar form by simply keeping the magnitude, keeping the phase angle, and throwing everything else away because it doesn't matter, okay? All right, so let's talk about how we go from rectangular to exponential or polar, okay? So we have a simple right triangle here. The magnitude of our complex number is found just by using Pythagorean theorem. So it's just going to be the real part squared plus the imaginary part squared is equal to the hypotenuse. So we could say that the magnitude of A is simply the square root of A squared plus B squared, or more generally, it is the square root of the real part of A squared plus the imaginary part of A. Sorry, let me close that parentheses. Squared. Okay. So literally nothing more than good old Pythagorean theorem for right triangle. Okay. Our angle theta A can be determined in a couple of different ways, but the one that I personally prefer is the inverse tangent or the arctangent of the imaginary part over the real part. So if we have a rectangular form complex number, we can get the polar form or the exponential form by simply applying these relationships, okay? If we had to do it by hand. There is a caveat to that I will talk about in a moment. that your calculators do not suffer from, which is why I think it's so important that you learn to use your calculators effectively. So now let's talk about how we go the other way around, okay? So these are just effectively trig identities as well. So the real part of A is just the magnitude of A cosine angle theta A. So that's just the projection of A onto the real axis. And the imaginary part of A is simply the magnitude of A sine theta A, or the projection onto the imaginary axis. So again, nothing that you guys haven't seen before in your prior math classes, because these are just simple vectors that we are manipulating, okay? All right, so does anybody have any questions about these relationships? Hopefully pretty straightforward. So I am intentionally going to show you something that is going to break this thing, okay? And this is why your calculators are so important. So let's say that I have a complex number x that is -3 plus j4. And I want to simply convert this to polar form. We're going to start doing this by hand, okay? So our magnitude of x would simply be the square root of -3 squared plus 4 squared, which is the square root of 25 or 5. We all okay with that? Our angle, theta x, is the inverse tangent of 4 over -3. So let me pull up that TI calculator real quick. Let me get rid of the key press history. So arc tangent of 4 over -3. So nothing crazy going on here. I'm going to press enter, and it gives me a value of -53 point something. Maybe it was 1, I don't remember. 0.13 degrees. Okay. Is this correct? So let's see. Here's my real axis. Here's my imaginary axis. So I'm going to go out -3 units in the real direction and up 4 units in the imaginary direction. So this is x based on my rectangular coordinates. According to my polar coordinates, I should be out 5, which would be here. So I'm just drawing an arc here. All of these are a distance of 5 away from the origin. And now I need to be at -53 degrees, which would be roughly here. So it looks like my hand calculation gave me something that is 180 degrees out of phase with what I'm expecting, or my angle is off by 180 degrees. So I can explain that very, very easily. My calculator cannot tell the difference. So tangent, inverse tangent of 4 over -3 shouldn't be equal to the inverse tangent of -4 over +3, but my calculator literally can't tell the difference between those two forms. Okay. So realistically, if we have the arctangent operation of our calculator will always return a number or an angle that is in quadrant 1 or quadrant 4. So just on the right-hand half of the plane. But we're going to be dealing with complex numbers that don't live there. So we need a better way to do this that isn't always having to think about where does this number live on the complex plane. So let me show you how this works on the TI calculator. Actually, I didn't even need to do that, sorry. So a better way to do this would be, I'm going to type in the number as a rectangular form complex number, right? So -3 plus 4. And then for you TI users here, this is why this is my favorite calculator. All of our complex number operations are literally on this pi button. And if we want to get into other things, we just press second and pi. So for me to get my imaginary operator, I'm just going to hit pi, pi, pi. So I have -3 plus 4i. Now I'm going to press second and then the pi button. And I'm simply going to scroll down until I hit this fourth option right here. So this is converting to a polar form. I'm going to hit enter. And now I'm going to hit enter again. And what I get is 5 with an angle of 126.87 degrees, which absolutely makes sense based on our plot of the rectangular form complex number. For what it's worth, by default, your TI calculators and your Casio calculators give you complex numbers in rectangular form. In electrical engineering, the overwhelming majority of the time, particularly when we're dealing with voltages and currents and things like that, we are actually going to be using the polar form of complex numbers. So it may be in your best interest to go up here to mode and look down here at this bottommost, I went too far, option where you can choose real numbers, rectangular, or polar form. I always have my calculator set for polar form as the default, okay? All right, so TI folks, you okay? I'm gonna transition over to Casio folks now, okay? So this is a Casio 115, which I think many of you have. I also have an emulator for the Casio 991. They are similar, but different enough that I'll show you the ropes here, okay? So for you Casio people, the first thing that we have to do is we actually have to set our calculator into complex mode. So I'm going to go to mode, and then I'm going to press option 2. Harrison, you have the 991, you might want to wait, since that's slightly different for you. So option 2 is for complex. Okay. So now that I'm in complex mode, I can do things. So I'm going to do the exact same thing I did, -3 plus 4, and then I press the engineering button to get my imaginary operator I. Okay. To access my conversions, I press Shift 2, and now I have the option of returning the argument. So that is literally just giving me the angle back. The complex conjugate operation, which I'll talk about here in a moment. Option 3 converts to polar. Option 4 converts to rectangular. I'm going to press option 3, and then I will press equals. And I get the 5 angle 126.869. For those of you with the Casio 115s, stuff like that, if you want to set your default angle, press Shift mode to bring up setup. Scroll down to the second screen. Option 3 is complex, and you can choose your default display to be either in rectangular form by option 1 or polar form with option 2. All right. Anybody with a 115 or equivalent calculator, so one of them that looks like this, have a question before I talk to my 991 folks? All right. Let me open up the Casio 991. That's the wrong one. Emulator. Continue with the current version. All right, so for those of you with a Casio 991 that looks like this, because there are a couple of different versions of 991s, we're going to have a similar path, right? We're going to press menu. And then, sorry, I don't know why the emulator I have has all of the language in Russian. I cannot change it. But the second option is for complex numbers. So now we're in complex mode. -3 plus 4 engineering button. And then for you guys with this particular calculator, or I think any of the 991s, the option button here in the top left is how you access all of your complex number operation options. So you have argument. I don't remember what option 2 is. Then you have real part, imaginary part. If we scroll down to the next screen, that's where we have our conversions. So I'm going to choose option 1 on the second screen to convert into a polar form complex number. I press equal, and wouldn't you know it, I get the exact same answer that I got on every other calculator. Okay. If you want to change your default angle settings, press Shift menu to go into setup, scroll down, complexity again, and then option 2. And I'm going to assume that you guys' calculators will have the menus actually in English. Yeah, so. All right. So how do you guys feel about using your calculators to convert from rectangular to polar? Pretty straightforward. Okay, so for what it's worth, if you want to convert from polar to rectangular, the process is fairly similar. So let's say that I just had a complex number for what it's worth that was, let's say 10 angle 15 degrees. You don't have to use parentheses all the time, but I'm just in the habit of doing it and it makes things cleaner and there are less mistakes. So I'm just going to do open parentheses 10. So to get the angle operator for the Casio 991s, I just press Shift and then the engineering key. I'm going to push 15 and then go back into my options and tell it to give me the rectangular form, which is option 2. And there we go. And to make it not look like that horrifying mess of stuff, 10 angle 15 is the same as 9.659 plus J 2.588. Okay. For the Casio 115 people, the process is very similar. Let me open that one up. And I don't know why it won't let me have both Casio things open at the same time, which is rather annoying, but 10. So for the Casio 115 folks, you get the angle operator by pressing Shift and then the negative key. And then we have our option to convert it into rectangular form, like so. And then for UTI folks, we get the angle operator by pressing second complex, and then our first option is the angle operator. And we get the same thing. Okay, so we've talked about converting from polar to rectangular, from rectangular to polar. So let's circle back around to normal, just talking about stuff. Okay, so before we get on to the mathematical operations that we are used to, I want to introduce a mathematical operation that is specific to complex numbers, and that is the complex conjugate operation. I'm going to erase this example stuff here really quickly. Okay. This is taking too long. delete. Okay. So complex conjugate. So if I have a rectangular form complex number, A is equal to A plus JB, or a exponential form complex number, the magnitude of A, e to the j theta A, or a polar form complex number, magnitude of A, angle theta A, I can define a complex conjugate operation as so, okay? So I'm going to put this on the graph. So all the complex conjugate operation does is it effectively just flips my complex number about the horizontal axis. So A conjugate would just be down here, where that asterisk symbol just means the conjugate of the complex number preceding it, okay? So when I flip that complex number over, does the real part change at all? Not even a little bit. The only thing that's going to change is that I'm going to go from an imaginary value of positive b to an imaginary value of negative b. So the complex conjugate operation for rectangular form numbers simply changes the sign on the imaginary part, okay? What do you guys think it's going to do for my exponential and polar form? Change the sign on the angle. That's it. Absolutely right. So angle A, e to the negative j theta A, or magnitude of A, angle negative theta A. That's all the complex conjugate operation is by hand. And you guys probably noticed when I was shuffling through the menus that your calculator can totally do it for you if you don't bother to learn this trivial operation. Okay. Okay, now let's get into the quote unquote normal math operations. So let's start with addition. Addition, we can pretty much only do using rectangular form complex numbers, okay? So let me rephrase that. By hand, we can only use rectangular form complex numbers. So if I have complex number A is equal to lowercase a plus JB, and complex number B is equal to lowercase c plus JD, then A plus B is simply A plus JB plus C plus JD. And I treat this just like any old vector addition, right? So I'm going to add my real parts together. I'm going to add my imaginary parts together. So I will have A plus C plus J, B plus D. Nothing particularly wild or crazy. Okay. Let's do subtraction over here on the right-hand side. So subtraction is literally just addition, except that there's a negative sign involved, right? So if I use those exact same complex numbers, A plus JB and C plus JD, then A minus B looks like A plus JB minus C plus JD. And so this returns A minus C plus J B minus D. So we simply just take the difference of the real parts and the imaginary parts and add those results together. So any questions, comments, or concerns regarding addition or subtraction? They work almost exactly as we would expect them to. Okay. All right, so when we hit multiplication, this is where things start to get a little interesting. Okay, so we're going to start with rectangular form complex numbers, multiplication. So A will once again be A plus JB, and B will once again be C plus JD. All right, so I need to make a note of the effectively how I'm going to express multiplication, okay? So whenever I'm asking you to multiply two complex numbers together, I'm literally just going to put them next to each other. You will not see a multiplication sign at all. So let me talk about why that is. I can't use an asterisk to imply a multiplication because that is the complex conjugate operation. I can't use a cross sign for multiplication because you might confuse that with the cross product operation, which does not exist for complex numbers. I can't use a dot to imply a multiplication because you might confuse that with a dot product, which also does not exist for complex numbers. So if you see two complex numbers next to each other, multiply them. Are we clear? Okay. So asterisk never, ever, 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 ever means multiply in this class. I get that all the time of, oh, I was doing these things and I got it wrong because you're not using the right damn operation. If they're just next to each other, multiply. If there's an asterisk, perform the complex conjugate operation to the one on the left. Okay. So we would have A plus JB multiplied by C plus JD. And so I'm just going to FOIL this out. So that's going to look like AC plus JAD plus JBC, excuse me, plus J squared BD. What's J squared? -1, right? So if J is the square root of -1, J squared is just -1. So this is actually going to look like AC minus BD plus J times AD plus BC. So we can see here that when we multiply two complex numbers together, we get a distinct real part and a distinct imaginary part, okay? Nothing too particularly difficult here. Ashton, you have a question? Okay. But things are actually a little bit easier for us if we do multiplication using exponential form or polar form complex numbers, okay? So over here on the right-hand side, let's say that I have A is equal to the magnitude of A, e to the j theta A, and B is equal to the magnitude of B, e to the j theta B. Well, when I try multiplying A and B together, I'm going to have magnitude of A, e to the j theta A, times the magnitude of B, e to the j theta B. Which just looks like the magnitude of A times the magnitude of B, e to the j theta A plus theta B. So multiplication in exponential form is just multiply the magnitudes, add the phase angles. In polar form, it's effectively the same thing, right? So this would be magnitude of A, magnitude of B with an angle of theta A plus theta B. Any questions regarding multiplication? All right, and so lastly, we have division, which pretty much sucks in rectangular form, but I'm still going to show you how to do it, and is incredibly easy to do in polar or exponential form. So let's look at division here relatively quickly. Okay. So once again, I have a complex number. A is A plus JB, and a complex number B is C plus JD. A over B would look like A plus JB over C plus JD. Now, there's nothing really wrong here, except that every other mathematical operation I have performed with rectangular form complex numbers has resulted in a distinct real part and a distinct imaginary part. And I don't have that anymore. I have a ratio of two rectangular form complex numbers. But I can make this give me a result in the form that I am expecting by getting a little fancy with the complex conjugate operation, okay? So if I multiply this thing by B conjugate over B conjugate, that would be C minus JD over C minus JD, like so. And so now I will have AC minus JAD plus JBC. So what's negative J squared going to be? Positive 1. So I'm going to just do negative J squared here, BD, and then I'm going to simplify things. So that's going to look like AC plus BD plus J BC minus AD. So I've got my numerators taken care of. In my denominator, I'm going to have C times C, so that's just C squared. I'm going to have a minus JCD, a plus JCD, and then a minus J squared, D squared. And very obviously, minus JCD and plus JCD cancel each other out. As we discussed a moment ago, negative J squared is the same thing as positive 1. And so what I'm going to do is I'm just going to get rid of that line across the whole thing, and I'm going to put C squared plus D squared here in my denominators. Okay. So multiplying my denominator by the complex conjugate of my denominator effectively gets rid of the imaginary signs in my denominator, okay? So now I have a distinct real part and a distinct imaginary part. As a quick aside, if I have the complex number A, and I take the conjugate of it, and then I multiply it by the complex number A itself, all this gives me is the magnitude of A squared, 100% of the time. Okay. So that is a kind of an identity that I will use at a couple of points in this class. All right, so we've got rectangular form division. As I mentioned, it is rather gross. Polar form division or exponential form division is incredibly easy. So if I have A is equal to the magnitude of A, e to the j theta A, and B is equal to the magnitude of B, e to the j theta B, then A over B just looks like magnitude of A, e to the j theta A over magnitude of B, e to the j theta B. And this is simply the magnitude of A over the magnitude of B, e to the j theta A minus theta B, or in polar form, magnitude of A over magnitude of B with an angle of theta A minus theta B. Okay, I went through that relatively quickly because I know I'm running short on time because of how much I've talked today. I will endeavor to get this video up very soon so that you can refer back to things. That being said, you are more than welcome to ask any questions that you have in the remaining 10 to 15 minutes of class. I went over how to do all of these operations by hand. I want to reiterate, I expect you to be able to just do them with your calculator, okay? So when you're working on the in-class assignment and all of that kind of good stuff, in the next 9 minutes, or if you choose to work on it at home or whatever, it is a calculator exercise, okay? If you have any questions about how to use your calculator to do the things, please, please, please let me know. And I may have gone over some of that in more detail in my video from last summer, just as a heads up. So, all right, I'm done talking about stuff for today. Enjoy 8 minutes of me not speaking.